Okay, thank you, Paul, for your presentation. I take over the screen. Now we take the lunch break, and at 1 p.m. Gerhard Rehm continue with the report dimension cross-laminated timber wall elements. Enjoy your break. Welcome back to the Dlubal Info Day Online. We continue with the next presentation of Gerhard Rehm, Design Cross-Laminated Timber Wall Elements. I hand over the screen to Gerhard. Gerhard, it's your turn.
Okay, perfect. Andrea, thank you very much for the introduction and welcome back to the Info Day afternoon. And today, or in the next presentation, it's all about cross-laminated timber. And I have decided to show a practical example. In this case, it's design of a deep beam element. So you see it here on the right picture. So it's it's a CLT element with big openings for the windows. And as you can see on the left picture, this wall is here behind this facade. And on the right side, we have nearly rigid support. And on the left side, we have a semi-rigid support here, since there is no column underneath this corner. Okay. Yeah, let's waste time. We start directly, in this case, in CAD work. And we see the model there. And let's have a look underneath the rendering. And we will see how it was solved. So you can see here the CLT slab or this, and here on the left side, of this problem. Okay, I got some issue with my monitor. So we beams and dowel type connection. So we get one component here in the vertical direction via this column, and one component goes in the upper chord to the next tension beam and downwards. So I'm interested only in I have some issues with my monitor. Wait a minute, please. Andreas, could you confirm, please, if you see still my screen?
I can see your CADWorks screen.
Yeah, okay. Okay, perfect. Yeah, I switched over the second monitor. There was an issue. Okay, let's see if it works fine. I'm sorry. The aim now is RFEM, and we can use it by export, for example, an IFC file, or we can export an DXF file, for example. But there's one smarter solution. So in this case, I will have a look only at this element here, and I will I'm interested in the center lines actually, because this is a solid element, and of course I want to design it with a surface element and not with a solid element. So therefore we need the center lines. And here in this case I can use a variant from CADWork. called, I was not able to rename it, but it called center surface for CLT. Okay, so I use it and select the element. And then let's go to the wireframe mode. And you can see here the center line or the center surface. And this is actually the one and only element I'm interested in. So I have the possibility now to export it as a file. In this case, I use the ACES export format. No, wait a minute, I need to, of course, select all of them. All right, I save it. Let's say export. And now I switch over to RFEM. Here I'm able to import this SAT file. Yeah, I select the Eurocode 0 plus for the SLS combinations, year 1990 plus year 1995, and we leave the global Eurocode, but of course you're able to select any other national annexes. Okay, we want to create load combinations automatically. I select it and I click OK. All right, then let's see what we have here. So you see it is, or the wall was overtaken from CAD work with the openings, and there is a material assigned. Okay, it's a softwood material, but it's not important for now. We will come to this later. We want to clean up the model a bit. So for example, I want to ignore this notch here on the upper right side. I will move this node to get a sharp, corner. Perfect. And I will do the same here. We have this tiny step here, or this tiny jump. I want to neglect it, of course. So I grab the C coordinate of this node and assign this coordinate to all other nodes. At the end, I will merge these nodes. And the same on the left side. Right side, I mean. All right, so now we can start actually by adding the loads, supports, and so on. But before we do this, let's think about what needs to be checked and what is important. You see here the rendering of this surface, and it's clear when there should be a support and on the right side should be a support that the outer layers should be orientated in horizontal direction. That's one important thing, that we need to take care of the orthotrophic direction. So the outer layers should be horizontal, and the other intermediate layers should be, every second intermediate layer should be orientated vertical. Okay, so the next thing is, of course, we need to take care about the supports. In this case, it's just, for demonstration reasons, it's a nodal support. We will not use it afterwards in our design, but for the slide, it is okay. Okay, we need to take care of the FE mesh. So what size should be used or is suitable? We talk about this. We talk about the stiffness of this element or of this CLT element, especially when we check this section here. So it's this one here is a section through the wall. We see here we have the horizontal layers, so these layers, and we have the transversal layers, which are orientated 90 degrees to the horizontal layers. And you see it here, this white area. This should be the space between this board and this board, because we do not use any glue, or we do not use any glue at the narrow sides of the boards. So this, of course, has influence to the stiffness, and we need to consider this correctly. Okay, we have a tiny notch here on the bottom. Of course, it will be not controlling since this beam is really high, or this element is really high in ratio to this small notch. But you can imagine when you have a CLT element as a beam, and maybe you can extend this line here, then you will see you have around 50% of the notch, and then it makes much more, or it is much more controlling, and this fact needs to be checked. And I'm just saying that you should consider it. Okay, because of the missing glue at the narrow sides, the shear cannot go directly from one board to the other board. It must go via torsion to the transversal layers, and from the transversal layers back to the horizontal layers. And this torsion, of course, needs to be checked too. Of course, we check our normal shear stresses, we check our normal stresses. Maybe buckling can occur. So in this case, we have roof beams and floor beams. So, but you can imagine when this acts as a one-span beam, the upper chord is under compression. So therefore, it can happen that the bottom side of this upper chord can buckle out somehow. This is a fact what we can check, or what we will check. And of course, the window must work also in the deformed shape, so it should not get any crack, or should not get destroyed. So therefore, we need to check the deformations, and especially the deformation inside here, and of course the global deformation. All right, that's so far because of my presentation for the slide side. And now, let's start directly in RFEM. So I will start really with nodal supports to see the effects. Okay, so I will support it on the left side. And of course, on the right side, I will use no degree of freedom in X direction. And of course, our wall is supported by the beams for the roof beams, the floor beams, and of course the walls. And in this case, I will directly add line supports. So I support it only in Y direction, means out of plane. So here, 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 and here. All right. So then, we can start with loading. So we create, first of all, load cases. So load case 1 should be self-weight, and we want to consider snow load. And of course, imposed load for the floor. Okay, you see here the load duration was assigned automatically, dependent on the action category. And now we start to fill the load cases with loads. All right, so for the roof, we have a line load of 5 kilonewton per meter. And for the floor, it is the same, 5 kilonewton per meter. Then for the windows, of course, the window has an self-weight as well, of course, which needs to be considered. Which ways do we have to fill loads for openings? There is here under tools, generate loads from aerial loads on openings. There is an option, but as you can see here, it distributes the load also to all boundary lines. And of course, this is maybe not the correct or the way what I want to consider now. I want to say that the whole window weight should act on this bottom lines here. So I use a normal line here. So when you consider we have a density of 25,000 Newton per cubic meter, and the height of the window is 1.83, and let's say 3 layers with 5 millimeters is 0.015. So equals around 0.7 kilonewton per meter. Okay, and at the end, we need, of course, to consider the weight, for the self weight of all components which will be fixed to the CLT element. And in this case, it acts on the whole surface, of course. So I use a surface load in this case. It should act in Z direction, and the load magnitude can be set here. In this case, of course, I can calculate it manually and enter the value here, but you can imagine if you do this really often, you waste a lot of time. So better to use here our multi-layer composition. Inside here, I have prepared a few compositions for the wall structure. So in this case, I use this setting here. Let's have a look inside. So there is an exterior plaster on the outside, wood fiber insulation. Then I have added the CLT. It should become 200 millimeter, and the density is 0 in this case because I consider the self weight of the CLT directly in my load case 1. So it's not necessary to add any value here, or you need to enter a value. 0, I guess it's not allowed, but just enter a small value like 0.0001 to get it directly to the graphic here. Otherwise, you need to delete it, and then you don't have this proper drawing. All right, then let's overtake this value and click OK, and here we go. So the next load case is snow load. So the snow load is 3.6 kilonewton per meter. And at the end, we have imposed load for the floor, and the floor beams are fixed on the bottom side of the bottom chart with 6.5 kilonewton per meter. All right, so far so good. We have finished loading, and we see directly the load combinations. Maybe you see here the 1.8. This considers the creeping effects. I forgot to switch this here, or to say you can switch the factor, the KDEF factor here at the properties of the national annex, and here on the bottom side you can switch, for example, to 0.6. So when you check it, you see the factor is considered in the load combinations for the quasi-permanent loading. All right, so then actually we can start with the analysis, and before we do this, let's check our FE mesh. So I just create the FE mesh and see what is the result. And as you can see, okay, the FE mesh is absolutely bad and needs to be optimized. So you see here it's the default setting of 0.5 meters, what we have in the background, or what we use in the background. But what FE mesh size should I use in this case? So the weakest point, I would say, or the weakest area is here, the upper chord, and I would say you should have at least 3 till 4 elements over the length of the height here of the upper chord. And with the background that we do not put any glue, or the producer do not put any glue on the narrow sides, and even they put glue on the narrow sides, I do not recommend it as a rigid connection since of humidity effects and so on. So because of this, and we check this distortion design, what I mentioned in the presentation, the board width or the FE mesh size should be the same width at the board width. So when you think about the ratio board width to board height around 4 to 1 or 3 to 1, then with a board width of with the board thickness of 40 millimeters, what is used in this example, and use 3 to 1, we get 120 millimeter board width. So I will use here, let's start with 0.1 meters and regenerate FE mesh, and we will see, okay, we got 4 elements we have this small triangle elements here and here. Yeah, for membrane forces, that's fine, but for bending, they could offer or could deliver some bad results. So maybe I will increase it a bit and see what's going on here. Yeah, 0.11. Yeah, looks good so far. So we use this half image size for the analysis. Okay, then just try to run the analysis, and then you will see we get an error message because of Poisson ratio. And yeah, when we see this is just a poplar softwood timber with an isotropic linear material model. Of course, we can change it here to isotropic elastic 2D, but in this case, that's something special with CLT, because for CLT, we have our add-on module called RF-LAMINATE. Okay, and inside the RF-LAMINATE, we define the composition. And afterwards, after we define the composition, before we run the analysis, the stiffness the stiffness gets exported to RFEM, and then the internal forces are calculated based on the stiffness what we exported. Okay, I want to design surface number 1 according to Eurocode for CO1 through CO5. So material characteristic, here we go with defining the composition. So we have to select the surface, it's surface 1, and here we can, for example, import compositions from different producers. Yeah, that's one way, and the common way actually to do not favor any producer, I created manually. In this case, this is what you can do too. So I'll load the material from our material library. So it's softwood, and I select, I choose a C24 in this case, and you see here all settings are filled. And in this case, I select here cross-laminated timber. And let's see what's going on here. We have the thickness, 40 millimeter is fine in this example. The values for EX and EY are loaded, and for shear modulus and so on. Here for the second layer, I hit the F8 button. It overtakes the entry from the first column. Okay, so in this case, the orthotrophic direction is 0 in this case. So you see here this coordinate system. The red arrow is the x-axis, and the green one is the y-axis. So if I rotate the second layer, for example, you will see the red arrow goes downwards, and this is the transversal layers, so the second one. Okay, and the same for the fourth layer. Okay, then let's go to the next tab. It's the material strengths. And here we simply modify the shear strength a bit because we do not consider any K-crack for surface design, and therefore I will modify it a bit and set it for all layers. Okay, the last tab is about the load duration class, but it was assigned automatically to the load cases, and therefore we always use the shortest load duration as the code offers, and it is assigned automatically. Here are a few settings about the service class, but this is fine for us. Okay, let's go back to the composition, and let's check the stiffness matrix. So we have the stiffness matrix for bending, the elements for bending, for shear, and for membrane. And in this case, I do not consider any wind, since the wind was really weak in this example, and it is not controlling for this example. It's much more easier in this case to consider and envelope the results. So therefore, in our case, only the stiffness matrix elements for membrane, means D66 through DA8, are necessary. Okay, but the only problem what we have now, we did not load it from the producer library. Therefore, we have a bit too much shear stiffness inside the plane, because how should the program know about the glue on the narrow sides? And this is what I want to show you about this issue. Okay. All right, so here I have prepared a small example, and these are solid elements. And in the upper one, I have no glue. Yeah, on the narrow, I have glue on the narrow side, so it means there is a rigid connection between the solids. And on the bottom side, you see I have modeled a small gap in between each board, from this point or from this direction, and also in the other direction here on the upper side. And here you see the results. So this is the result from the solid, and this is the result from the surface and RF laminate. You see the result is the same. And of course, if there is no glue on the narrow sides, yeah, of course the deformation gets bigger, yeah, and this effect needs to be considered also here in RF laminate. And what you need to do is you need to consider the ratio from this solid element to this surface or this solid element. And then you get a factor and you know how to reduce the stiffness. Of course, this is really time consuming, and nobody wants to do this. Fortunately, there is an approach already, and it's based in the Austrian National Annex. So here you see this Excel sheet. You can download it afterwards on our homepage. You see here a small table, and you need to enter just the thickness of the slab. You need to enter the amount of layers and the board width, and you get a reduction factor of 0.59. And when you enter this value here in the details of the composition, as you can see here, you get exactly the same deformation as the solid elements has. So this needs to be done in case the producer does not provide us any values, but normally they do, and therefore you don't have to waste time for this. All right, so let's go back. And for our example, we need to figure out these factors. So I'll open the Excel sheet. So in this case, we had 200 millimeters, 5 layers, and 120 millimeter board width. So we have a reduction factor for the torsional stiffness, it's 0.5, and for the shear stiffness, the in-plane shear stiffness of 0.6. And these values we overtake now. So it's 0.5 and 0.6. I use it also for the bending or for the torsional element, since we do an eigenvalue analysis afterwards, and there the torsional stiffness is important too. Okay, here I say I have no glue at the narrow sides. You see there is an A modulus in Y direction considered. We will check what happens afterwards, and we have 120 millimeter board width. That's because of this torsion design. As you can see here now, the A modulus in Y direction of each layer, so not of the whole composition, only of each layer, is set to 0. All right, and then let's start the analysis. Okay, so this is the result. The first time really confusing, but let's see what we can do. So in this case, or in this example, in this tab here, you can select which designs you want to see. And in this case, we have only membrane forces, so the stresses are constant over the width, and therefore I'm interested only at the results from the middle layers. And of course, I'm only interested in our normal stress and in our shear stress in plane. That's XY, that's refer to the local axis system. And afterwards we activate the torsion design, but for now it should be fine. Okay, then we come down to a ratio of 5 point something. Okay, let's see where it happens. You see this black arrow here. Of course, it's exactly at the location where the singularity is. and where the nodal support is. And of course, everyone knows who dealt already with FEM, that's a typical singularity, and we cannot evaluate these results. Okay, so what we can do in this case? Of course, we can do the same as we do for loads. We distribute it to line loads or area loads. So in this case, I will distribute it to a line load. No, wait a minute, it was the start. Support width is here 22 centimeters. Okay, so let's start here with the line release, with the line support, and of course, yeah, we should release it in X direction, and I create only one support, and yeah, it should be, of course, supported in X direction. Therefore, I enter a tiny spring here in X direction. Otherwise, the structure would move to infinity. All right, then let's go back to RF-LAMINATE again and check what happens. Yeah, so we had a ratio of 5 point something, and because of the line supports, we came down to 0.99. Of course, when we check the maximum ratio again, it comes from CO4. Yeah, maybe the easiest way, or I will remove all other COs for future analysis, because CO4 in this case is design giving, and I will check only CO4. It saves me a bit of time. Okay, so we have 0.99, and when we check it, it's not in the corner, but it's here. Yeah, so we have no stiffness here on this line, but then we have a really stiff support or a rigid support, and of course we get another singularity here. Of course, in case we use this approach, we have to consider, okay, what about our support reactions? So I will check our support reactions, and yeah, we can see here, maybe we need to refine the mesh a bit, but you can see it here, also tension forces are covered by the support. Of course, this should not happen in our example or in general in timber. Therefore, I add here a nonlinearity, which says, okay, please fail if there is a negative support force. So in case of tension, the forces should fail. Okay, then let's check it again, just to avoid any restraint here in this corner. Okay, then we are fine, perfect. Okay, but yeah, let's go back to CAD work, and yeah, let's see here. This it is considered, or the support condition here on the left side is still considered as a rigid support. Maybe that's true here for the right side, but of course not for the side. How we can represent this support in our 2D analysis. And I have prepared a scene in CAD work, so these are my elements of interest. And in this case, I can simply say here, please export a module structural system. This is what I want to do. Okay, there's something about the connection. I want to save it, let's say desktop. And I want to save this submodel DSTV file on my desktop. And now I can import it also here on the left side, CADWork STP file. So that's not, it's an STP file based on this interface for steel constructions, but it works also for timber. Okay, so, oops, here we go. So we don't need any load combinations, and we can simply import this file. Okay, looks good so far. So we have, the member elements included to the RFEM, and let's see the wireframe model. You see, there are still a few issues. We need to fix this, or we can fix it quickly here. So you see here, members are not connected, or members are too long, and so on. That's because of the half width of this beam element. Okay, so this one we will fix via drag and drop directly, and the same on the right side, and here on the left side. Okay, then we quickly support it. So we need to support it in Y direction, otherwise the beam would rotate around their own axis. And there is another support underneath this and this column. So I will add another one, which is sliding in Y direction here and here. And the top short, of course, must be supported, otherwise it will fall down or the beam will rotate around the own axis. Okay, so in this case, I need to restrain it around Y-axis, for example, with a spring. And here I want to support it in X direction. For simplification, I just select it for all nodes, but I'm only interested in the vertical deformation. And you see here, the vertical deformation is sliding, which is fine. Okay, and what is my aim now actually? The aim is I want to add a unit load here. And based on this unit load, I get a deformation. And based on this deformation, I can calculate my equivalent spring. So I create a unit load of 1 kilonewton. I deactivate the self-weight in this case. Please see 1 kilonewton. And let's see about the deformation in C direction. Okay, I forgot. Okay, I forgot to mention here we have some hinges and we have here some beams. Maybe I explain it more in a better way. So in this case, I directly replace these beams by truss elements. So with a hinge connection on member start and member end. And here these coupling members, which considers the eccentricity. The hinges come directly from CAD work, but I don't want to consider it. Therefore, I will delete it. Okay. And of course, you can discuss if this is a truss beam or maybe better to use a tension beam. But in this example, we get only tension forces. Therefore, it does not matter. Okay, we get a deformation of 0.147 millimeter. And of course, we can use now the spring. But of course, we know there is an OSB sheet on this beam elements. So we can add this OSB sheet too to have more stiffness. This is what I will do now. I will create a new surface. So we have timber, OSB, and here we select wall stress. Should have 15 millimeter OSB 3 sheet, 15 millimeter. And in this case, of course, we cannot use an isotropic linear elastic material model. We will switch over to orthotropic elastic, where we have different E modulus in different direction. Okay. So here we go. On the left side and on the right side. Okay. Then let's run the analysis. We get an error. This error is because of this tension beams or this truss beams. And you see here, there is no node, there's no connection to the beam, which is fine. But of course, there should be no connection to the surface as well. And in this case, the easiest way is to say, to the surface, okay, please do not integrate this line, and then the member is not integrated automatically too. I will do the same on the right side. Okay. And now let's run the analysis again. So we remember we had 0.14 millimeters. And now it comes to 0.89 millimeters. Okay, the FE mesh can be optimized. Let's switch this to 0.89 2 meters. And let's run the analysis again, should not have a big influence. So we still have 0.9 millimeters, hopefully 0.09 millimeters. Okay, and in this example, of course, the OSB sheet is connected rigidly to the beam elements. Of course, that's not the truth, because yeah, each timber element is connected to other timber elements with an elastic spring, for example. And this is what I want to consider too. So for this case, I will select only 2 surfaces and all integrated objects. Okay, so and now I want to release the surface from the beam elements, and this I can do with this line releases. So new graphically, and here I define a spring. So I want to say here the axis system should be according to the z-axis coordinate system. So in this case, I can consider x and y degree of freedom. So the spring constant, of course, it depends on the fastener. In this case, some staples. So the case there for one staple is around 500 Newton per millimeter, and when you use 10 staples per meter, you get 5,000. So 500 by 10 staples per meter. The same here. Okay, in both directions, and here I release surface number 1. Surface number 1, and perfect. I select all these lines, and I do the same on the right side. So this is surface number 2, and now we should get a deformation which is between the 0.09 and 0.14. Of course, it is in this case it's 0.10, and finally we will add another semi-rigid connection, of course, because of this tension beam connection with this dowel type fasteners. So in this case, I select these beams and I say, okay, please use a beam element, and I want to define some member and hinges. Okay, so I have prepared an Excel sheet where we can simply calculate this spring. So for example, this is the result for dowels from Eurocode 5, table 7.1. Okay, so for one dowel type fasteners with 12 millimeters, we get a spring of around 4,500 kilonewton per meter. And this value can be multiplied by 2 because of steel wood connection. And we have 2 shear planes and 25 fasteners. So we get a spring of 450,000 kilonewton per meter, which is really rigid. So in this case, it should be in Y and Z direction. So 450,000. And here, we can consider just a tiny spring to keep it stable. And of course, on both sides. So we had 0.10 millimeter, and now it should become a bit higher, a bit much more deformation. So 0.32 millimeters. Let's get back to our Excel file. And here, I divided the 1 kilonewton divided by the 13.2 millimeters, and I get this equivalent spring for the whole support. And here I distribute this spring along the line length. It's 22 centimeters, and I get this spring 35,000 kilonewton per meter. Okay, and this spring I will enter in my main model. All right, I will change it here. So in Z direction, I want to consider this value. Perfect. Of course, here on the right side, it's different because here we have a column underneath with 22 by 22 centimeters, and it's, I guess, 3 meters high. Yeah. So in this case, we can calculate an equivalent spring 2, and in this case, the program makes it easy. We can use this function wall in Z direction. So the width was 220 millimeters, the height was 3 meters. Material, in this case, timber, it has different modulus in a different direction. Therefore, until now, the timber material is not supported by this function, but we simply use a concrete material, a lightweight concrete in this example, which has the same modulus as the beam has, as the timber has. Okay, and should be hinged, and I get here my equivalent spring. Okay, so in this case, it will not work because I don't want to consider, of course, the spring in X direction. Therefore, I will deactivate it and I will replace it again by 0.01. Okay, that's it so far. And let's add maybe here this nonlinearity. Okay, and let's get back to the RF-LAMINATE module. And finally, let's check the results. Okay, we came down to 0.96, but when we check it, it's not here on the bottom right corner, it's here in the windows, because of course we have some singularity here because of the corners here. Okay, but so far it's good. So now we need to evaluate the results. And for the surface design, we need to go away from thinking about member design where we have a clear ratio. Because of the singularity, I recommend you following procedure, what you can do. So it makes no sense to check here the smiley if it's red or green. You need to evaluate it at once. In this case, let's check about let's start here. So we have, for example, layer number 1. Of course, we have only one layer side for the results because the results are constant. We are the width. We have no plate stress and no load out of plane. So therefore, it makes us easy. It makes it as easy. Okay, let's check the stresses in this case. So this is the typical normal stress. So where there is tension and here compression on this chord and the same on the upper chord. So, and we can see directly the ratio. So the ratio here is around 0.6. So even if there are singularities, I would say for this ratio, this is okay, this is fine. For shear, so let's check the shear force or the shear stress. Of course, the shear stress is really high here in this region and this region, which makes sense because of, there is less high than here or here. And let's check the ratio. But we know only the ratio is really close to 1. But the question is only in which areas. And this is exactly the way or what you should consider. You should consider which areas are affected. And in this case, I recommend, okay, please show me all ratios which are higher than 70%. And then you will see, oh, there is actually nearly none, but only here, because that's clear, it's a singularity. You see the stresses, they become really large within one FE element. So here we exaggerate the 70% ratio. So only these corners have higher ratio, but we cannot evaluate it. There are a few possibilities how you can get rid of the singularities. I don't want to show it in detail now because we have showed this so often in our webinars. And the easiest and a good way is to use this average regions here. So you can create a new average region for surface 1. And the center, for example, should be here. And should be a circle with 0.3 meters. And when I click OK, and let's check us the results for CO4. So in this case, I want to check the shear, for example. And you can see here, when I deactivate the average region, this is the result which comes from there. And when I activate the average region, you see the result was distributed along the length or the height or width of this average region. Of course, better to add here a mesh refinement to get a finer mesh around these nodes. So this is one option, but I don't want to get in detail for this example or for this average regions, because there are so many information on our website about this, and you find it also in our other webinars, how we deal with this average regions. Okay, so then let's check here this notch result here, and in this example I will create a simple section, and the section should start here and should go to 5.5 meter for the surface number 1 in, let's say, -c direction. To increase this section. No, wait a minute. Of course, the section must go out of the plane, and then you see exactly here this stress. Okay, maybe better. So in this case, I used NY. So maybe better to use a finer FE mesh here, and then you get this typical, transversal tension curve, which is shown here. And I don't want to go in detail for this example because RF-LAMINATE is evaluating this automatically. Because we have our stresses. So when we check, and I need to switch. When we check our, that's okay. When we check our normal force inside here, inside Y direction. So Y direction, as you can see here, it goes perpendicular to the horizontal layers. So this can be evaluated manually. We have this section, for example, or you can simply, let's do the job from the RF-LAMINATE module, which is doing this automatically. Okay. So then let's go back to the RF-LAMINATE module again, and let's run the analysis again, and let's see the results again. So this is actually really simple because we have only membrane forces. You can imagine if you have plate bending and normal forces and so on, a lot of more design checks must be done for this example, but in this case it's really easy. So we have only our normal stress, our shear stress, and the accordingly ratio. Of course, I did not activate it. We need to activate this torsion design because of the missing glue on the narrow side. So this is what I want to do now. I will activate it, and here you see the design is not fulfilled, but please think about the ratio and where the ratio is. So we go to OK and see, okay, maximum is 1,335, but as you can see, it's here at these spots. So for this example, I would say I would not define any average regions, because you can argument, okay, when I check everything what is bigger than 1, so a ratio 100% till 133%, you see, okay, the whole surface is fine, only this one is not fine, and vice versa too. So if you are interested in everything what is fine, just go from 0 to 1, for example, and then you see the ratio, the real ratio. Only here in these elements you will not see any ratio, but of course you are not interested in. Unfortunately, we have no possibility in timber to distribute any stresses to fix the singularities, or to distribute the stresses with a plastic analysis, so a nonlinear plastic analysis, since we use only a linear elastic material behavior in timber, which is actually common. So there are no real there is a way to check it also for timber. We have here a solid called new material model called orthotrophic plastic 3D, but this is not the wished design for this simple wall element, because it is much more. So you need to define just the strengths, the limits, and of course you need to model the slab or the wall element as a solid element. So each layer needs to be modeled separately. You need to consider to model the gap because of the glue on narrow sides or no glue on narrow sides. This is not a practical way to do this. Okay, then let's check. SLS is missing. Okay, but yeah, stability. Okay, so let's check about stability of this wall. So I keep it simple. In this case, I start my add-on module called RF stability, and where we get let's check maybe where we have the highest normal forces. So we go here to NX, and let's see. Okay, we have around 580 here from CO1. CO2 is 806, and CO3 is 996. Okay, I guess the other one will not get any higher. So let's use CO3 with the highest normal force in this area, because I believe that the first eigenshape will happen here in this area, which is clear actually. Okay, let's go back to our stability and select CO3 and simply run the analysis. And the only information what I get out is I get the eigenshape, which is okay. So this is the first eigenshape. Yeah, so it can happen that this bottom chord will buckle out somehow, but of course we need to check the critical load factor. And here you see the critical load factor is 30 or nearly 30. That means you need to increase the load by factor 30 to get this failing of the bottom chord. So you need to analyze stability, because this is on the unsafe side, because no imperfections are considered and so on. But we have a good feeling with this factor, because it is common to use a factor of 0 from 1 to 10. We can or we need to check stability, and everything what is getting bigger than 10, we can think about to neglect it, and in this case we definitely can neglect it. So okay, how we deal with stability design for the surface elements I have shown on the website for cross-laminated timber. So simply go to dlubal.com. I need to switch to English, and then go to support and learning, and here knowledge base, and here you can, I'm not sure if I find the correct keyword. Maybe better to search my name instead. Okay, seems there's some issue with the website. I cannot search for it, but it doesn't matter. Okay, you will find this information. If not, if you don't find it, please contact us. I will send you the links afterwards. Okay, then at the end, and there's not much more time anymore, but I will show you in a few minutes, so I will need 5 to 10 minutes more. I will show you about this serviceability stuff, what I mentioned in the presentation. Okay, so let's check. In this case, let's focus on CO8 only. So CO8, that's the deformation, the characteristic deformation with snow load, or maybe the other one is more important. because the imposed load was higher than the snow load. Okay, so let's check the deformation of this element. All right. Okay, so yeah, do not wonder that deformation is displayed with factor 67. Yeah, so therefore it's clear that the deformation is higher here on the left side because this support is weaker than the right support. Yeah, but as you can see here, yeah, this window is already deformed. And of course, when you think about a rectangular window, this rectangular window must fit into the hole after it's deformed. And of course, it should not become any load. And how we can deal with this, I will show you now. So in this case, yeah, of course, you can, for example, analyze or export. You can export this deformed shape to AutoCAD or to a CAD file, to a DXF file, and there you can insert this window and check if it's correct or if it's fit, if it still fits inside. But there's a much more smarter way. In this case, I will add some rectangular surfaces. In this case, I will use a rigid surface. And here too. And of course, we cannot run the analysis now because this would be too much, or there would be too much stiffness. So what we need to know is, okay, every window is built in with some gap between window and wall. And we can consider this too. So I will simply see the local axis system of the lines. So this is axis system of the surface. I will switch it off. Okay, it's all about the Z direction of the lines. And in this case, I can use this line releases too. So I see here new graphically. Okay, and in this case, X and Y direction. So out of plane and in X direction. I use a tiny spring to keep it stable. Otherwise, this rigid surfaces would move to infinity. So I will fix it with a tiny spring. And in Z direction, I say here the option or the nonlinearity partial activity. And inside here, I can define some slippage or displacement in this case. So let's say 1 centimeter. Of course, you can do it differently for different directions. So in plus and minus, for my example, it's fine with both directions. All right. So I will release surface, I guess it's number 2. And I want to release these lines. And I want to release surface 3 for this one here. Okay, and now let's see. Run the analysis again. Okay, so I didn't remember about the deformation before, but that's actually not the aim. Let's check the deformation. So first, you see, or you might see it a bit, it could be a bit confusing because the window, is displayed inside the CLT wall, but that's clear. We model everything, or we have modeled the window, the rigid surface, directly to this wall element. So we do not model the gap, we consider it with a line release. And therefore, okay, the distance now between this node and this node must be smaller than 1 centimeter. Yeah, you can imagine it's hard to evaluate, especially on bigger models, or especially when you need to check it with some line or some diagrams. You can do this and say, okay, please show me the result diagram, and on this line or on this section, okay, what is the deformation, and compare it and so on. This is actually not a good idea. Much smarter is to use here our results called releases. And here I can activate the releases and I get the release forces for line releases. So in this case, I get the deformation UC, for example, and you see the deformation. So here the deformation is 0.1 millimeter. So the limit is 1 centimeter, so 10 millimeters. So we are absolutely fine, yeah, in this example. So this is the way you can check it, yeah. So you see directly which deformation you get, which relative deformation. And yeah, another option is to check the forces. So we check VC, and as you can see here, VC is 0. And of course, if there would go some forces into the window, into the rigid surface, we would see any force here, and we would see any distribution of the force here. So therefore, yeah, it is fine. And yeah, this is the way we can check this this stuff here. It was clear that the deformation is not getting so big, but on bigger elements and so on, this could be an issue and could be solved. So because of this, you have to think about the gap between the window and yeah, the window and the surface, or the window, the real window. Okay, so from my side, I finished this presentation. Hopefully it was a good help for you for your future, yeah, for your future structures. And yeah, thank you very much. We will have a short break, I guess. And afterwards, I will show you something about vibration design in timber. Okay, let's go back to Andrea. Thank you very much.